This video is going through some examples and past exam questions for solving simultaneous equations using matrices. Firstly, we'll do a quick refresh of how we set up simultaneous equations in matrix form. So the first thing you want to look at is how many equations do I have and how many variables or unknown values am I solving for, and that will tell you the size of your matrix setup. So here we're looking for x and y, and so we've got two unknown variables. So if we've got two unknowns, that means we're going to set up a 2 by 2 matrix for our pronumerals, the numbers in front of the letters. Then we're going to set up a column matrix containing those unknowns, so a 2 by 1, and finally another column matrix containing the answers. So we take this, our 2 by 2 matrix, our 2 by 1, and our answers. In our 2 by 2 matrix, we're taking firstly the values of x and y, the numbers in front of x and y. You may want to fill out that column matrix first, and that will help remind you of the order that you are working across. And remember, everything in this first equation will sit in the first row of our matrices set up there. And so we're going to put into row 1, column 1 of this square matrix the number 5 that aligns with x, and then moving across to row 1, column 2, we put the number 2 as that corresponds with the y. So this multiplication of 5x plus 2y equals 21. So 21 goes in our answer matrix in that row 1, column 1. And then we'll do the same thing for the second equation. So we have 7x, so 7 in that row 2, column 1, 3y, so a 3 in row 2, column 2, and that 7x plus 3y equals 29. So that goes in our row 2, column 1 of our answer matrix. And so there's our setup. When we go to solve this, remember if we're thinking about this as being in the form A times x equals c, to get our solution for that column matrix x, we are going to pre-multiply by the inverse of A. So we're going to do inverse A times c. So if we write that down in our setup, we're going to have x, y equals our inverse of our square matrix. So in our notation, remember we put that as to the power of -1 times our column of answer matrix. And so from this point, if we're just solving it, we can put it into our calculator. We don't have to calculate what the inverse is, but we may choose to. And so when we put in our answer, we will be able to get an equivalent matrix for x and y. So let's put that in our calculator now. Okay, so putting our matrix in, firstly, remember we can go into this little shortcut to get our matrix templates up. We put in that first matrix, 5, 2, 7, 3, and I put that to the power of -1. So I get the inverse times my answer matrix, so my column 21 and 29, and when I press enter, I get the answer there, a column matrix, 5 and -2. And so returning back here, 5, -2, and remember we're saying that these are equal matrices, so that tells us that x is equal to 5 and y is equal to -2. If we have the scenario where we've got 3 equations, like in example B here, firstly just check how many pronumerals or how many unknown values do I have. So I can see that there is an x, there is a y, and there is also a z. So I've got 3 unknowns. And so that means my setup of A, X, C is going to be a 3 by 3. My pronumerals are going to be in a 3 by 1 column, and my answers are also going to be in a 3 by 1 column. And so again, if we take this information and set it up, if in this case I do fill in my pronumeral column matrix first, so I can see I've got X, Y, and Z, that can help me keep track because not each of those equations has all 3 letters in it. So we're working our way across the equation and working in the same order every time to go through the pronumerals. So in that first equation, X, I have a 2X. I have no Y, so I don't leave a gap, but I put a 0. And I've got 1Z. Remember, no pronumeral means it's 1. That first equation is equal to 5. So in the first row of that answer column matrix, I put a 5. If I move now on to the second equation, I've got 1x, I have negative 2y, and there are no z's. So I put a 0 there. And that equation, I'm told, is equal 0. Finally, the third equation, I've got 0x, I've got 1y, and I've got negative 1z. And again, working across, that equals negative 1. The same process to solve this. So x will equal the inverse of matrix A times the inverse, times matrix C, our answer matrix. So if we write down our working, I can say that x, y, z is going to equal this whole first matrix to the power of negative 1 for the inverse, and multiply that by our answer matrix. So again, at this point, we will go to our calculator to get that answer. So again, going into our template, but this time I need to pick up the one that allows me to create any size. Okay, so a 3 by 3 is the default, so that's good. We put in that matrix of pronumerals, so 2, 0, 1, 1, negative 2, 0, and 0, 1, negative 1. Remember, to the power of negative 1 to make it the inverse. And now multiply by our answer column matrix, which is a 3 by 1. And our values there were 5, 0, and 1. Press enter and I get my values there. Now, my calculator settings are in auto. So if it is a fractional answer, it will give it as that. If we wanted those as decimals, remember we can just press Control and enter, and that will give us the approximate or decimal values. Okay, so just be careful about what the question is asking you to do. Here I can give decimals because they are exact values there. Okay, writing out my answer. So I'm going to put them as the decimal values. So 2.4, 1.2, 0.2. And a reminder, that is just our matrix answer, but our final answer will be x is equal to 2.4, y is equal to 1.2, and z is equal to 0.2. Always remember to take your final answer out of that matrix form and state it. So now moving on to some past exam questions. This one from the 2017 Northern Hemisphere exam. And so we're told Yvette needs to buy a total of 9 pens and markers. 5 pens and 4 markers will cost her $31. Whereas 4 pens and 5 markers will cost her $32. So let P be the cost of a pen, M be the cost of a marker. We're asked to consider the following matrix equations and decide how many of these equations could Yvette use to solve to get a matrix that contains the price of a pen and the price of a marker. So firstly, let's take this information and convert that into equations. So if we're told 5 pens, so 5p, and 4 markers, 4m, is equal to $31. We have 4 pens, 5 markers is equal to $32. So our obvious setup, if we just take these equations and think of how we would set it up in that form, A times X equals C, we would have 5, 4, 4, 5, P, M, and 31, 32. So that's just a straight conversion from the equation into that matrix form as we see it. First equation on the top row, second equation on the bottom row. Now, here, all 4 of these solutions or options have got PM as the leading matrix there. So remember, in order to get PM on its own, we would have to take the inverse of our pronumeral matrix across, so the inverse of A. Now we would need to check what our inverse is before we can eliminate any of those options there. And it might actually be quick and easy to actually get what the determinant is of that matrix. So let's just find firstly our determinant of A. And so remember, your determinant is always the values of A and D multiplied minus B and C. So we're going to do 5 times 5, take away 4 times 4. And so what have we got? 20 take 16. Sorry, 25 take 16. So our determinant is 9. And so that means when I'm doing my inverse of A, if I just pop that over here, would be swap the positions, swap the signs, and everything divided by 9 or multiplied by that determinant on the outside there. And so if we look at the options that we've got, this first option here hasn't even found the inverse, but the notation is correct. So from our setup that we originally had, that gives us one option. This second set of equations here, the order that this inverse matrix has been brought across is incorrect. Okay, so the order is not correct there. So we can't use that one. With these final two, you can see that they've got a determinant and or have multiplied it in. So let's look at the setup 4 first. Here, actually in 3 and 4, you can see the solution 32 is on the top line. Okay, so that means instead of the setup I have at the top here, they've actually turned it upside down. So they've got equation 1 on the bottom row and equation 2 on the top row. So that changes all of this setup that I did up the top. So in order to work out if that answer is correct, I actually need to change some things around, and it will affect my determinant as well and my inverse. So let's switch those around. So I would have 4, 5 equals 32 across the top. And then the second equation, 5, 4 equals 31. My determinant now has also changed, 4 by 4 minus 5 by 5, which is -9. So one option is to have the determinant on the outside, so -9. Remember, we switch the positions of A and C, so they're both the number 4, so that doesn't look like a change. And we change the signs of B and C there, so it becomes -5, -5. And so when we look at this equation setup 3, I can see that that matches, so that's an option. And if I look at equation setup 4, I have the wrong order of pronumerals here to match that 32 being on the top. So out of the 4 equation options, I have 2 that are suitable to match the setup that Yvette needs to solve. So that means out of my options here, I have C as the correct answer. Okay, this next exam question, a little bit easier than the last. In a game between two teams, Hillside and Rovers, each team can score points in two ways. The team may hit a full or the team may hit a bit. So we've got two different options there. More points are scored for hitting a full than for a bit. A team's total point score is the sum of the points scored by hitting fulls and bits. So we would have however many fulls plus however many bits would equal our total. We've got a table here showing the breakdown of the scores. Let F be the number of points scored by hitting one full, and B be the number of points scored by hitting one bit. So let's put this information from the table together into some equations. So Hillside has scored 4 fulls and 8 bits for a total of 52 points. Rovers, 5 fulls, 2 bits for a total of 49 points. So there's our equation set up. We're now being asked to find which would be the matrix product that could be used to find matrix F and B. So again, if we're going from our version of setup, A times X equals C, we want to get our answer matrix. So we want to get X on its own, which means we're bringing the inverse of A across and multiplying by C. We have two equations with two unknowns. So we also know we're going to have a 2 by 2 inverse and a 2 by 1 column. Okay, so we're looking for that format. So knowing that, I can say C is not an option, D is not an option, and E is not an option because those three don't have that correct setup with those correct orders. So out of our two options here, A and B, we're looking to see, is there the inverse represented? And so if we go back to our equations, and if I was to set up that matrix that matrix A, I would be saying I have 4, 8, 5, and 2 times FB, and that equals 52, 49. To bring that inverse across, I would have that first square matrix to the power of -1. And so I can see here, B just has matrix A, no inverse, okay? And so that's not correct. And the option A does have the inverse brought across, multiplied by the answer. So that's our correct response there. Okay, so our final example. Solution of simultaneous linear equations is determined by evaluating the matrix product. One of these linear equations could be, so we've got our matrix product set up and we're asked to go backwards to figure out what could have been the equations that we put in. Now, before we get too excited and think it's nice and easy, remember what we have here is our matrix equation setup has already been converted. So what we actually have here is our inverse of matrix A, not the original pronumerals. So if we already have our inverse, I need to get back to my original matrix. And the way that we do that is by using index laws. Our original matrix A, our original pronumerals, is just like that matrix to the power of +1. Okay, so no change. It is just what it is. So to get back to that, with index laws, if I raise a power to another power, what I actually do is multiply those powers together. So when I do an inverse and I inverse it, what actually happens is I get back to my original value, okay? Because -1 times -1 is +1, and that's the same as going back to the original matrix itself. So what we need to find is the inverse of that inverse matrix there. We'll use our calculator for that. Okay, so just entering in that matrix of -4, 3, 3 again, and -2. And we want to do that to the power of -1. So we're getting back to an original matrix of 2, 3, 3, 4. And so now if we take that information and write out our equations, what we're saying is we've got 2x, 3y, and that equals, from our answer matrix at the top, 3. The second row, I've got 3x, 4y, and that equals -1. And so then when I look at my answer options, I can see that C is the correct answer there. It's the only one that represents this matrix form. That's it for this section. Make sure you do go back through and work through some of those questions and look for some of the challenging questions in Enrollo as well, and add some additional notes to help you when you hit little questions, particularly like this last one that can be a bit challenging. All right, thanks.